Chapter 2, Video 1. We're going to look at 3 different ideas involving analyzing distributions. All right, so let's say you got your Chapter 1 AP Stats test back, and you got an 85%. Great job. How did you do, though, compared to the rest of the class? Well, you might ask, in Chapter 1 we learned about mean and median, measures of center. So you could ask, well, what was the class average? And then you would know, am I above average, am I below average? But there's a different way that we could also kind of compare your score against other scores. And so what we could do is look at all the data. And so here's all the test scores, and we can see you're 85% there, and all the ones that are in red are the people that did better than you. And all the people that were in green, you did better than them. So in the end, when I count up everything, I see that that you did better than 12 other people, and you did worse than 7 other people. And you might go, but those two numbers only add up to be 19, and there are 20 numbers up here. Correct, you are the 20th number that's missing. So what we can do is look at an idea called a percentile. And I'm sure you've probably heard of this term before, especially if you were given back standardized test results. You may have been told that you were, your math scores were at the 90th percentile or at the 80th percentile. When you're a baby and you're going to the doctor every 3 months, 6 months, and then you start going to the doctor every year, they start measuring your height and your weight. And they might tell you, if you're a big baby, you might be in the 90th percentile for weight. Or if you're a small baby, you might be in the 25th percentile for weight or height. So we need to define what exactly is a percentile. And so the definition we're going to use is the percent of values that are less than or equal to a specified value. So when we look at your score of 85% on the first chapter test, it was as good or better than 13 out of 20 or 65% of all scores. Therefore, we can say that your score of 85% is at the 65th percentile. Now, keep in mind, if someone else also scored an 85, you would also include that other person's 85 as a part of your percentile because you did as good as that person, and we would include them, right? Because we're going to say or equal to, not just the people that you did better than. So I've got a quick you-do problem. The person who scored a 65% is in what percentile? And is it possible to be in the 0th percentile? And is it possible to be in the 100th percentile? So consider what would that mean specifically if it is possible to be in the 0th percentile or to be in the 100th percentile. All right, the next topic we're going to take a look at is we've technically already talked about percentiles back in Chapter 1 when we talked about the first and third quartiles and the median. When we looked at a box plot, the box plot split up our data into 25% chunks. From the minimum to Q1 was 25%, Q1 to the median was the next 25%, the median to Q3 was the next 25%, and Q3 up to the maximum was the final 25%. So Q1 is at the 25th percentile because there are 25% of values that are less than or equal to it. The median is halfway in our data set, and halfway is going to be 50% of our data is less than or equal to the median. And Q3, there's 75% of values that are less than or equal to the third quartile. So we have this new type of graph called an ogive. And I have no idea how ogive relates to its proper name, which is a cumulative relative frequency graph. No idea how those two things are connected, but here we are. So an ogive, or a cumulative relative frequency graph, is a graph that displays a distribution's values versus the value's percentiles. So what I want you to notice is we have height of 1-year-old boys in inches. And this is actual data that I took from the World Health Organization. And all ogives start in the bottom left corner because we're going to start with the smallest values. And where would we expect the smallest values percentiles to be? Well, near 0, right? So we got to have basically like the minimum, the smallest or not smallest, the shortest height for a 1-year-old boy is really going to be down here. There's the minimum shortest kid, is basically going to be down there towards the 0th percentile. And then as we talk about taller and taller and taller and taller kids, we start to get more and more and more data, and then we can start to increase our percentile until we get all the way up to the tallest 1-year-old kid, who is as taller than all the other kids. And so the vertical axis here represents our percentiles. And initially, they may not look like percentiles because they may be written as decimals instead of, 10th, 20th, 30th, like we would normally expect to see percentiles written as. But just know that, 0.2 is the 20th percentile. The 50th percentile would be right here between 0.4 and 0.6. And so that's how we would kind of initially look at this graph. We'll have our actual data values on the horizontal axis typically, and we would have the percentiles as the vertical axis. So the median is how tall for a 1-year-old boy? Well, remember, we mentioned before, the median is the 50th percentile. And the 50th percentile is going to be right here between 0.4 and 0.6. So how I use the graph is I would need, ideally, some sort of straight edge, maybe a ruler, and I'm going to start at the 50th percentile, go all the way across until I hit the ogive, and then I'm going to drop straight down from there. And then what I need to do is estimate, because it didn't hit at an exact number there, but it looks like it's in between, this would be 29.5 right here. So this looks like it's roughly almost in between 29.5 and 30. So I could say my best guess is 29.75 inches. Some of you might go, it looks to be a little bit more than that. Could I say 29.8 inches instead? Absolutely. We're just guessing here, right? Based on our best idea of what is in between those two. So honestly, as long as you give me anything that is reasonable in here, then you would get the credit for it. All right, the next question we're going to take a look at is a 29.25 inch baby is in what percentile? So when we did the median, we started on the vertical axis. We shot over horizontally until we hit the ogive, and then we shot down vertically to see what actual data that would match up with. Well, we can also go the opposite way. We can start on the horizontal axis. So let me throw these over here. And so if I wanted to estimate 29.25, one thing I can already look at here is 29.75 was the median, which again was the 50th percentile. So if I have 29.25 and that is smaller than 29.75, I know based on the median being 29.75, a 29.25 inch baby is going to be below the median. It's going to be something smaller than the 50th percentile. So let's see what exactly that comes out to be. So 29.25, that would be right here, right in between 29 and 29.5. Now what I would do is I would go vertically up until I hit the graph, so right there, and then I would want to go horizontally over and see where approximately does that hit the vertical axis. And I'd say that is very, very close to the 30th percentile. And you might go, well, it looks like it's a little bit less. I agree, it does look like it's a tad bit less, but you know what? A nice round number looks like the 30th percentile. Now, one thing that kind of amazes me is that just being a ½ inch shorter than the median at the 50th percentile took us down 20%, right? So that means 20% of babies between the 30th and the 50th percentile are only a ½ inch apart from each other, from 29.25 to 29.75 inches. All right, so now I've got a couple you-do problems for you to try with an ogive. So you do number 1 for ogives. What percent of 1-year-old boys are between 29 and 31 inches? You're going to have to kind of do a little double time work on that one. Likewise, what is the IQR for all 1-year-old boys' heights? So you're going to have to remember what was the formula for IQR from chapter 1. And again, you're going to have to do a little double work to be able to figure out what those values are so that you can calculate the IQR. And the last topic we're going to take a look at. Personally, I'm going to share it with you, I scored a 1240 on my SATs back in the day. And I scored a 27 on the ACT. Now, you might think, that sounds kind of low. And I think it kind of is. But you know what? I got a 36 on my math part of my ACT all 3 times I took it. I just really suck at English and reading and science. But I'm really good at math. So everything averaged out to be a 27 in the end. Now, if I wanted to know which test did I do better on, did I do better on my SAT or my SAT? Well, I need some more information. I need to know what was the mean and the standard deviation for each of those tests. So on the ACT, the mean score is an 18 and the standard deviation is 6. Now, I know I did above average with my score of 27, right? And on the SAT, the mean score was 1,000 with a standard deviation of 200, which, again, my 1240 is also above average. It's above the mean. But if I want to compare 2 different things, kind of on 2 different scales, if you will, because right now I'm trying to compare apples to oranges. But if I want to be able to compare apples to apples, I need to do a process that's called standardizing. So I'm going to standardize my ACT score, and I'm going to standardize my SAT score so that I can actually compare them to each other. So we're going to calculate what's called a z-score. And a z-score is nothing more than how many standard deviations a value is away from the mean. How many standard deviations a value is away from the mean. And so this formula, our z-score formula, is going to equal to x, and that is the particular value, that'll be my score that I got, minus the mean score, divided by how much a standard deviation is worth. Now, I will tell you, on the AP Stats exam, this formula is not given to you. So this is definitely going to be something that would be on you to memorize. And I will say that this formula is used kind of throughout the year, especially when we get into second semester stuff. So it's going to be something that's going to stick around. So z-scores can be calculated for any shaped distribution, as long as we know the mean and the standard deviation. Now, I mention this now, and this may seem kind of weird, like, why is he mentioning any shape? Well, later this chapter, we're really going to put a lot of focus and emphasis on normal distributions. And what I've seen over the years is that once we get to talking about normal distributions and doing calculations with normal distributions, then typically students think that z-scores can only be calculated for normal distributions. And that is simply not true. So any shape distribution, skewed left, skewed right, uniform, bimodal, whatever the case may be, we can always calculate a z-score if we have a mean and a standard deviation value. So let's actually calculate it now. All right, so I need my ACT score, which again was a 27. I need to subtract away the mean ACT score, 18, and divide it by how much a standard deviation is worth. What is that average difference between each value and the mean, which is 6. So if I take 27 minus 18, that gives me a value of 9, which I need to divide by 6, which gives me, what is that, 1.5. So that means my score of 27 on the ACT is 1.5 standard deviations above the mean. Now, is it possible to get a negative z-score? And it is. And that would happen, if you think about it, is if your x value was smaller than the mean, then it is possible for this to be a negative value. And a negative value would indicate you were below average. You were below the mean. All right, let's do the same thing with the SAT score. So I scored a 1240 minus the mean of 1,000. So I can see right there, I am 240 points above average. But again, if I want to be able to kind of compare this apples to apples, now I'm going to divide by the standard deviation. So 240 points above average, when a standard deviation is worth 200, then, I don't know, what does that come out to be? Let me grab my calculator. What do we got, calculator? 240 divided by 200, and it's 1.2. So now this is saying for the SAT, my score of 1240 was 1.2 standard deviations above the mean. So which test did I do better on? Well, technically, I did better on the ACT because I was more above average on the ACT than I was on the SAT. Now, does that mean the greater the z-score, the better overall? And so that's one thing I want you to think about, and we'll discuss in class the next day. But is bigger always better in terms of z-score? And I'll give you a hint. Think about certain types of, sports or different types of data that you could collect where maybe bigger isn't always better. Maybe you want a smaller number that would indicate quote unquote better. So think about that problem, and we will discuss it the next day in class.